So, hi everyone. Welcome to my talk today. My name is Matthew Bresciani, and today we're going to talk about how to choose the right heading source for your next PX4 platform. So, I'm Matthew. I'm working at Autyrion for the last 5 years, and I'm also a maintainer of PX4 since then in the dev team. And I've been working with PX4, I think, for the last 7 years now. All right, so at first we're going to talk about some definitions about what's heading your course and angles like that, to try to understand how to differentiate them and which one we care. Also, why do we need a good heading estimate for a drone? And we'll briefly discuss about the steps to initialize the EKF we have, so the navigation filter we have in PX4, and how it links also to the heading in that talk. Then second part will be about heading sources. There are many ways to find the heading, to measure the heading for navigation. And here we're going to discuss about 3 of the main ones you will be able to use on a drone. So yeah, the first one is the magnetometer that you all know. The second one is dual GNSS compassing. And the third one is more software-based thing where you assemble IMU data with GPS to find the heading. Then we'll discuss a bit what are the pros and cons of each of those, also how to select them, and try to understand like what are the influence of the drone itself, especially based on electromagnetic interference you have on drone, and hopefully that will give you some good tools to choose the right one. So first, we have different angles here. We're going to talk mainly about the heading. So the heading, what is if you look from top of a vehicle, the direction of the nose of the vehicle with respect to north is the heading. So it doesn't matter if there is any wind, if there is external forces, the heading is just the orientation of the vehicle from a view from top. Then, for example, you also have like the course. The course is usually defined between an origin and a destination point. So between 2 waypoints, there is a certain course, which is the angle of that path relative to north, and the bearing is usually the current course of the vehicle. So it depends on where you are and where you go. So if you have no wind, for example, usually heading and the bearing here will be the same, but as soon as you start to have some wind, the vehicle will start to slip, and then they will be different. Another one that we also use quite a bit is the yaw. Sometimes also in PX4 we mix them up a bit. There is a reason for that, is that so the yaw is the rotation about the z-axis in a Euler sequence, so yaw pitch roll or roll pitch yaw or whatever sequence you're using. And in the specific case that we also use in PX4, which is yaw, pitch, and roll, then the yaw is actually the same as the heading. So that's why we can say or yaw or heading. But that's only true if you use that rotation sequence. So why do we need a good yaw estimate? The point is that we have a vehicle that has sensor that reads measurements in the body frame of the vehicle. And when we want to navigate, we have to transpose that in an inertial frame that is usually north-oriented. And that way, if it's north-oriented, we can attach it to a map, and so we can define missions with respect to north, and then also fuse measurement like longitude, latitude that you get from GNSS. So first you get your body frame measurement, you can rotate them in an initial frame, and then you can integrate them in case of the IMU here, and afterwards you can fuse other measurements that are referenced in a local frame, in a north-oriented local frame here. Also, what's important to note is that we can continue to estimate the heading and other angles like the roll and pitch of the vehicle by just integrating the gyroscope. But the problem is that it's a relative measurement, or we integrate a measured velocity, and that drifts over time. It can drift for different reasons. So the sensor can have a bias that is not well calibrated out. There can be a change of temperature also that change the bias. Many different things, and to try to constrain that, we want to fuse an absolute measurement of the heading. So those are the main reasons why we want a heading source. Now, here quickly about how we initialize a Kalman filter, like the different steps we have. That's not true for everything, but that's at least the steps we use in PX4 here. So first step is that we want to find what's the tilt, the current tilt of the vehicle. That's directly done at boot. As soon as you plug on the vehicle, it does that quickly by looking at the accelerometer data. If there is no external or little external motion, motion of the vehicle, what you measure is actually the gravity vector. And by measuring the gravity vector, you can roughly know what's your tilt. That's not really accurate, especially if the operator is manipulating the drone. But that's usually good enough to give you like plus minus 10 degrees of tilt. Second step, what we do is that it's called fine leveling. And to do that, we use a kind of software trick that is called a quasi-stationary alignment. So we fuse a constant position. We tell the drone that it's not really moving right now. That's the assumption, with some level of uncertainty. And the equation of the Kalman filter will actually optimize to improve the tilt accuracy estimate, such that the actual navigation result will not drift away. Then here comes the heading. So we have a measurement. Usually it's from a magnetometer or a GNSS multi-antenna system, and there you align the heading. And as soon as all those three first steps are done, you can actually start to use some other external sources of position and velocity that are defined in a north-aligned frame, such as GNSS. So which different sources we have for heading? First one is the Earth magnetic field. So we have to think about we have the Earth. We can think about having a magnet at the center of the Earth that will kind of give us some reference, and we can measure it with a magnetometer to try to find what is the north. We have to know that the strength of the Earth magnetic field is quite weak compared to everything else we have on a drone. So for example, the Earth magnetic field is between 0.25 to 0.65 Gauss. And if you compare that to a fridge magnet, which is 100 Gauss, so no wonder why if you have like a small magnet next to a magnetometer, you can't even read the magnetic field of the Earth. Also, there is an inclination component, so the Earth magnetic field is not parallel to the curvature of the Earth. So the more you go north, the more it will actually point down in the Earth. So you only have the Earth magnetic field that is parallel close to the equator. And for example, here in New Orleans, it's 58 degrees downwards. So 50 degrees, it's from the horizontal. So it's actually quite tilted down here. And there is also a declination component because the geographic north and the magnetic north, they are not exactly at the same place. So depending on your actual longitude and latitude, you will have a different declination. In PX4, what we do, because what we care actually is about the true north. So we have world magnetic model tables that we bake in the software. As soon as we get some data from the GNSS sensor, we can look up those tables, and then we can correct the magnetometer measurement to actually find where the true north is. You can also find all those data online. So there are calculators where you can just input the location you are. And that's often also helpful when you debug logs to just look at how it's expected to be in the region where you're flying, and then you can compare if you really have that on your measurements. So how do we measure it? Usually we have magnetometers. There are 3 main types. We use in aviation, there are many more, but the main types are Hall effect sensor, the magnetoresistive ones, and the flux gate. In PX4, we mainly have Hall effect sensor and magnetoresistive one. The reason why we usually don't have flux gate is that the price is much, much higher. So for example, like a Hall effect sensor is about a couple of bucks, while a flux gate is several $1,000s. So normally it's not really worth paying for a flux gate, except for some situations. And that picture explains a bit how a Hall effect sensor works. So basically what you do is that you input some current in a conductor, and depending on the magnetic field, that will push the electrons to one side, and that will create a potential difference. So you can measure a voltage that depends really on the strength of the magnetic field. So the different source of magnetic field you can have, or you have a permanent magnet that will just like create a permanent magnetic field, or you can also have it generated from wires. So usually on drones, from power cables, they will as soon as there is current flowing through them, they will generate a magnetic field that can also influence your magnetometer reading. And for that we call hard iron disturbances, because they are all the same, so they create a bias in your measurement. So as soon as you have some of those on your drone, you'll see that if you do, for example, a full turn on the drone, normally it should trace a perfect circle that has the radius of the Earth magnetic field strength where you are. But if you have a magnet or something that creates some magnetic field, that will shift the whole circle, so you will see some offsets. And that's why you have to do the calibration beforehand. Calibration works well, again, if it's constant. If it's not constant, for example, power cable, calibration usually doesn't work so well because usually it moves. Current is not always the same. Second type of disturbance you have that you can calibrate is the soft iron effects. So different material have different properties. Some are diamagnetic, paramagnetic, or ferromagnetic. The worst one you have is ferromagnetic, because they highly distort the magnetic field. So basically they are the magnetic field that goes near to them will, instead of continuing like their straight line to the air, they will go inside the material. So they will be rerouted on the vehicle. So if you have a lot of parts with iron or nickel on the drone, the problem is like it will distort all the magnetic field, and it will be harder to actually find what's the correct orientation of the drone. That usually just squeezes out that circle. So we can also calibrate that for that. And if it's not moving on the drone, usually it works quite well. And if it's a moving part, then the calibration doesn't work out because it's time dependent again. So a lot of problems with magnetometer, a lot of things to be careful. And so second technology we can use for heading is using GNSS RTK compassing. Basically what it does, probably most of you know about just the normal RTK, where you have like a ground station that is stationary, that has a well-known position, and that one will compute a correction and then send it to the GNSS receiver that is on the drone. And then by doing those correction, you have much better accuracy. Here in that case, we have both the base, which is now called moving base, and the rover on the drone. And by doing that, we don't have an absolute position that is more accurate than the normal GNSS sensor. However, we have a super accurate differential position. And by knowing what's the difference in latitude and longitude of both of the sensor, you can figure out what's the heading of the drone. That's highly dependent then on the baseline, which is the distance between the two antennas. So it works well if you have a large vehicle, because you can have a reasonable baseline that should be at least 20 centimeters to get some good accuracy. It works really well. People use that on rovers or cars or boats, because you usually have enough distance for that. And especially rovers, and they have bad magnetic field readings also close to the ground, so that's pretty good for rovers. And of course, that you need also good satellite connection directly, so it won't work indoor or where GNSS doesn't work in general. Third one, as I say, it's more software thing, so it's basically based on a Kalman filter. The principle is that you have, again, your body frame measurement that you integrate in a local frame. So you assume that you have your current heading, you integrate that, then you get some update from a GNSS receiver. And by doing that, the Kalman filter will figure out how it can minimize the error by adjusting, for example, the heading. So you can, that's exactly what you do if you're following, for example, your Google map. You haven't started yet. You don't know. Sometimes the arrow is wrong, and you think you're going in some direction. You look at it, and then you will see that you're actually going in another direction. So you stop, you correct. That's basically what it does. So it's it tries to figure out what's the correct direction depending on where you are. Yeah. So that works quite well. It can work with IMU GNSS, but you can also use different type of body frame sensor. For example, if you have wheel odometry or optical flow sensor, that will also help to figure out what's the direction. And you don't need also to have GPS if you just care about like what's the heading bit, not relative to north, but relative to any local frame. For example, if you have some vision thing, it will also estimate the heading, the correct heading relative to the origin of the vision navigation system. So how to choose now? Yeah, so that's a bit the problem that you have on a drone, is that everything is influencing the sensors. Everything is really close together, even on those big drones, for example, here. So as soon as you have motors, then in motors you have magnets, you have high currents, you have speed controllers, you have power cable running through the arms. Here, for example, you also have another payload that will generate some magnetic fields, also some electromagnetic interference. So as a rule of thumb, so every time there is high current, that will produce a magnetic field that will affect the magnetometer. And every time there is high frequency switching, for example, in the wireless communication or in the speed controllers or cameras, that will affect the GNSS reception. So you have to figure out it's not usually the best place, but the less worse place to put the sensor on the drone. Oops. So they have different advantages and disadvantages. So for example, if you plan to fly sometimes in some GNSS denied areas, you better have a magnetometer during that time to still contain the heading drift. Otherwise, you can just use GNSS compassing, for example. Also, the problem with if you want to do GNSS compassing is that you need some motion. Otherwise, you can't figure out what's the correct orientation. Also, it depends a bit if your application, if you're operating near metallic structure. For example, if you're operating close to the ground, also usually there are reinforced concrete that has a lot of iron in there that will disturb the mag field as well. And also the cost, because for example, magnetometer compared to dual GNSS, it's not the same price tag. And also the calibration, magnetometer you need to calibrate. You can calibrate some errors. If it's changing over time, you can't recalibrate them. And the selection tree here, it's quite simplified, but basically if you have a variable magnetic environment, if you don't have it, then use a magnetometer because it's the cheaper and the simplest solution. Otherwise, if it's a static application and you have problems with the mag field, you pretty much have to go the route of dual GNSS sensor. And otherwise, it depends a bit if you can rely at least on the mag field before takeoff or not. I'll explain a bit that later. And otherwise, if you can't really rely on that, but you accept that the user will be able to take off in a manual mode or, for example, altitude mode in PX4, you can do INS GNSS compassing because you can just take off the drone, move a bit, everything will align, and then you can switch to a position mode or autonomous mode. So for magnetometer, I'll give some details. We have here like the mag type called auto. So we robustified a bit the usage of the magnetometer because we've seen so many problems that actually people, they have the drone that aligns properly on ground, but as soon as it starts to take off, there is a lot of influence from high current in the wires, and that really disturbs the magnetometer. And actually, when you are moving, when you are flying, you don't really need the magnetometer anymore. So you only need to initialize, and you only need it if you wait for a long time without motion while being in the air. So what we've done here is that we only use the mag field to initialize, and then we let the EKF do its own INS GNSS compassing that it actually does naturally. So you don't need an extra filter for that. So the EKF will figure out itself, constraints the heading estimate, and we only use the magnetometer again if we see that the uncertainty on the heading is getting too large. Also during the flight, we continuously estimate the magnetometer biases, even if we don't use them, so that as soon as you have to use them again, they are more or less calibrated, freshly calibrated from the flight. And yeah, that's the default type, mag type we have on PX4 1.14 now. Thank you. So if you have some questions, yes?
So will it seamlessly switch? Say we took off with dual GPS spread, and we're using that, and then we end up in a situation where we're in a GPS denied area, and we have compass on board.
Yes.
Would it switch automatically to use compass, or would it just do what?
It will switch to magnetometer, yes.
And we can fly in and out of that port?
Yes, exactly. So as soon as you, normally if you configure the GNSS compassing, it has a higher priority. So when that runs, we stop completely the other part. However, as soon as that one stops by itself, for example, if there is no data or the quality is too low, you can't use it, it will automatically switch back to magnetometer mode. Yes?
So for GPS denied, do you have any comments about using multiple magnetometers, like 3 or 4, within the same platform?
You mean that to average, for example, all the errors? So I think that could be a solution. However, the problem is it's already hard to usually place one magnetometer well. So I see the point where you might want to place several of them. But as I said, usually you don't really need them when you fly. So it could be an option, I think, for certain cases. But usually if you can just initialize with the mag and then you do a normal thing like doing missions and you're not just hovering for 1 hour without moving, usually you don't need extra magnetometers. So often I would say it's not worth the effort of trying to put several magnetometers. Yes?
Yeah. If you set the EKF mag type to none,
yes.
How long would it need and how much motion would it need to begin having a decent heading installation. And I asked you this because we are setting up a plane with a runway takeoff, and it's a concrete runway, so there's steel that is disrupting the magnetometer. And if we have the magnetometer enabled and set it up to take off towards the waypoint, the way it does, it's using the magnetometer rather than PX4s. And this makes it veer off the runway due to the interferences.
Yeah.
So we were thinking about disabling it,
Yes.
but we don't know how long of motion it would need to have an estimation and be able to actually go towards.
Right. So that actually highly depends on the acceleration you have. So if you have high acceleration, then we have, so it's not directly the EKF2 that will initialize. In the special case of MagType known, what we do is that we have another special filter that is actually a multi-hypothesis filter. So we have 5 different EKF that will start in different direction. And as soon as you start to move, some will converge super quickly, some not because they are further away from the truth. And that we've seen, for example, for drone, if they start to just accelerate a bit, that usually takes like 1 meter to converge. And so it's quite quick. So if you have runway takeoff and the initial acceleration is high enough, normally you should be able to get a good heading estimate in just 1 second. If it's gradual, that's a bit of a problem because there will be too much noise compared to the actual signal you get from the IMU. So then it might take longer to initialize.
Yeah. Okay, because right now our options are setting either to none
Yes.
for the magnetometer,
Yes.
or to take off at a fixed heading that I think will use more of the gyros.
Yes. So also, otherwise you could take off manually if that's an option for you. And as soon as you do the first turn, for example, it will, of course, initialize because you have some lateral acceleration. And then you can switch to autonomous mode.
Thank you for the insight.
Will this happen in version 1.14 or is it earlier?
So the MagType non is there since at least 1.13, at least, probably even before. However, like all the changes I told about for MagType Auto, that's recent. That's only on 1.14. So before, when you decide to use Mag, it was always using it, even if you realize it's not so good. So you had like some toilet bowl that will not resolve by itself. And now, for example, if you have a wrong initial heading estimate, it can be off by even, I tried up to 45 degrees, and it will just like make one circle and then fix itself. So yeah, that's 1.14 only. Yes?
Can the system detect when the magnetometer goes bad as a result of flying close to a metal structure?
Yes, so also that's what we added for 1.14. We monitor the actual the innovation. So the innovation is the difference between the measurement and the prediction from the estimator. And if that one is too large, so if there is too much innovation, there is no good consistency, we say that the sensor is bad, so we disable it temporarily until there is again some good motion, and we can say that, okay, the innovation is now low, so we can restart. For example, if you move away from that metallic structure, then once you move, then the heading is observable through GNSS INS, and then you can figure out if it's again correct or not. And yeah.
As a follow-up on that, during that period when the magnetometer data is disabled, is heading estimation performed just by dead reckoning?
Yes. So it's dead reckoning, yeah. And if you have GPS again, if you have a bit of motion, then it will just constrain the heading drift. Yeah. Yes?
Do you have any experience with shielding for improving magnetometer performance?
Shielding. So shielding, you can't shield the magnetometer itself, of course, but you can try to shield as much as possible. For example, the wire cables. or the ACs, but usually it's a ton of effort to do. And normally shielding we do for electromagnetic interference for the GNSS. So that's usually, for example, if you have a camera or a high-speed port connection like USB 3, usually try to shield that, because otherwise you have no reception at all from satellites. But shielding mag field is quite hard. So yeah. Yes?
What about larger vehicles? I guess in your opinion, this is the recommendation, if you got something, not massive, 50 to 100 kilos, 50, 70 kilos, maybe the only situation, or the only scenario that works is something like a dual GPS heading source.
Yeah.
I mean, you can't, how do you do magnet something that weighs 70 kilos?
So actually, if you just want to initialize the heading, you could do the magdens by just doing one turn on one axis, because you don't really need the other axis. So I would say for a larger vehicle, if you want and if you can actually use the mag, just do the calibration on the one turn.
Is there a setting for one axis though?
I think there is a calibration setting you can, yeah. Normally you can choose between 6 axes, 3 axes, or even less. So yeah. I haven't tried myself, but that's what I would suggest to do. All right. Yeah. Thank you. So I'm still available if you have any questions, if you want to discuss anything about EKF, I will be around. Thank you.